Okay, so hello everyone. As said, I'm Alex, I'm from Imperial. I'd like to talk to you about recent work I did with Derek Lee, who's in the audience, and Frank Schindler on Lindbladian versus Postselected non-Hermitian topology. So I'll begin with a bit of motivation. The first is that as this session's topic is on non-Hermitian topology, non-Hermitian Hamiltonians have been investigated. However, it's known that non-Hermitian Hamiltonians can't be interpreted as many-body operators. So we asked a simple question, which is, do topological phenomena exist in proper open quantum system dynamics, such as the simple case of Lindbladians? And the punchline of this talk is that, yes, that's the case, and that a given target post-selected non-Hermitian Hamiltonian can have different Lindblad topologies. In particular, there are full phase transitions, such as a reversal of the non-Hermitian skin effect, which occur in Lindblad systems and that are hidden by post-selection. Okay, so given that the previous talk did introduce the Hatton-Nelson model, I'll be quick on this. But in non-Hermitian Hamiltonians, we consider Schrödinger dynamics under some Hamiltonian H, which is non-Hermitian on the top left here, meaning that the ket psi of t loses amplitude in time. And the one-dimensional Hatton-Nelson model is basically a non-Hermitian tight binding model on a one-dimensional chain of spinless fermions. It's non-reciprocal in the sense that we have stronger, by convention, stronger hopping to the right as t plus g, where t and g are real parameters, and hopping to the left goes as t minus g, which is less than t plus g. And so unfortunately the GIF doesn't work, but the goal of this GIF was to show that an initial perturbation on the left moves as a wave to the right in time, and this shows that this is a characteristic of the non-Hermitian skin effect, which is that in open boundary conditions, your eigenmodes localize at the right edge of the chain, compared to periodic boundary conditions where they're delocalized. And this is known to have a topological origin in the sense that if we compute the Bloch Hamiltonian of the Hatton-Nelson model, we know that its spectrum in the complex plane, shown on the right here, is an ellipse, and has a winding number as a function of k, the quantum number associated with translational invariance in periodic boundary conditions. And in open boundary conditions, there's a stark change in the spectrum. It's just a line, the red line here. And it's known that this winding number is rigorously related to the presence of a non-Hermitian skin effect. Okay, so now the Lindblad equation. So on the top left here is one version of the Lindblad equation. So previously I showed Schrödinger dynamics under a pure ket state. Now we consider density matrices, rho, whose dynamics is dictated by curly L on rho, which dictates the time derivative of rho. And one version of the Lindblad equation is written here, where the first two terms on the top left are post-selected dynamics, where H post is a non-Hermitian Hamiltonian. And the last term is a quantum jumps term, which goes as Jm rho, Jm dagger, where Jm's are the quantum jumps, indexed by some label m. Now, H post, we know, can be expressed in terms of the Hermitian Hamiltonian evolution of the system itself, and also the quantum jumps term. These quantum jumps dictate interaction between the system and the environment. One can understand Lindblad dynamics by so-called stochastic unraveling, where we consider individual so-called quantum trajectories of pure states, psi of t, which undergo two steps. The first is that psi of t evolves under the non-Hermitian post-selected Hamiltonian. E to the minus I h post t is the unitary evolution up to normalization. And then stochastically, at random times, we have quantum jump events, shown on the middle right here, where we basically act the JMs on the psis. Post-selection therefore means that we select the quantum trajectories for which no such jumps occurred, meaning the second part of this stochastic algorithm does not occur. One interpretation of the Lindblad equation is therefore that H post dictates non-Hermitian hopping, such as the Hatton-Nelson model, shown on the bottom chain here. And the JMs are jumps that, again, dictate interaction with the environment. For example, if we consider spinless fermions, Cm, annihilation operators, then the JMs can be superpositions of the Cms, or C daggers for gain. Okay, now we ask, well, what about Lindblad topology? So in order to study topology, we mean the skin effect here, which is dictated by the density evolution. So we define the correlation matrix delta sub ij, where I and j are site labels, which is the trace of C dagger ICJ rho. And it turns out that from the Lindblad equation, one can derive the equation of motion for this correlation matrix, and it's shown on the top right here. Now I introduced two new matrices, HF, which we call the effective Hamiltonian, to be distinguished from the post-selected Hamiltonian, and M superscript G, which is the gain, which is due to gain in the system, which I won't discuss further due to time. Of interest is this HF matrix. So if we compare to H post, the non-Hermitian post-selected Hamiltonian, for quadratic systems with U1 conservation, we can define a similar single particle post-selected Hamiltonian, H post sub ij, which can be, for example, the Hatton-Nelson model. And importantly, we find that HF is not the same as H post when both loss and gain are present, which means that Lindbladian dynamics are dictated by this HF, and it's generically different to H post, and that's the surprise, which is that HF can have a different winding than H post. So we can see this in a specific example. Here we consider a specific system where we want to realize the Hatton-Nelson model as the post-selected non-Hermitian Hamiltonian. So here we choose a Hermitian Hamiltonian H, which is just a nearest neighbor tight binding model. And the loss operators on the top left, Lm, go as Cm minus I Cm plus 1, up to some factor. And gain jump operators are another set of jump operators, which goes C dagger, M minus I C dagger M plus 1, up to some factor. On the bottom left here, we show the spectrum when loss is dominant. So on the first plot is the winding of H post, or rather just the spectrum of H post, which winds as expected for the Hatton-Nelson model. HF is different, but it still has the same winding number direction in the anti-clockwise direction. And when gain is greater than loss, in figure B on the bottom right here, H post still has the same Hatton-Nelson spectrum, which means it winds in still the anti-clockwise way, but HF has the opposite winding direction. Now it's clockwise. So this is the big surprise. And what is the consequence for this for the dynamics? So again, the GIFs were supposed to work, but unfortunately I'll just describe them. For loss greater than gain, when we consider a perturbation that occurs on the left, we see, just like the Hatton-Nelson model, that it moves to the right, meaning that we have a localization of eigenmodes on the right. And when gain is greater than loss, meaning we now consider, when we consider gain is greater than loss, it turns out that perturbations move to the left. Now, again, the GIF was supposed to show that the steady state of this system is actually above half filling for gain greater than loss, and therefore the perturbations should be interpreted more as whole perturbations, and they move to the left, which is dictated again by the opposite winding number of HF, the effective Hamiltonian. So in summary, we've studied we've compared non-Hermitian Hamiltonian topology to Lindblad topology. We know that non-Hermitian Hamiltonian topology only makes sense as a single particle phenomenon. We studied Lindbladian topology and made sense of it, and we know now that this can be fully many-body and therefore supersedes non-Hermitian Hamiltonian topology. We found that a target post-selected non-Hermitian Hamiltonian can have different Lindblad topologies and full phase transitions that are not encapsulated by the post-selected Hamiltonian. And as a conclusion, the topology of open quantum systems should be studied with Lindbladians. So I thank you for your attention, and a reference to the paper and a QR code is shown. Thank you.